Okay, in this example, we want to look at a circuit that has a different kind of source. So we've primarily been looking at circuits that have just a DC source with a switch at t equals 0, which is just a step function on the source. In this case, our source is sinusoidal. So first of all, we're told that all of the initial conditions are 0. So in other words, we have no initial stored energy. That means the initial voltage on the capacitor is 0 and the initial current through the inductor is 0. We have a sinusoidal voltage source that is switched onto the circuit at t equals 0. So we will be able to do the Laplace transform of the sinusoidal source because it is switched on at t equals 0. So that is this source right here. So this is the circuit in the time domain. When we transform to the Laplace domain, the capacitor is going to go to a capacitive impedance 1 over SC. The inductor is going to go to an inductive impedance SL, and the voltage is going to go to its Laplace function in the S domain. So here's that. Here is the transform of the cosine function. Here is 1 over SC. Here is SL, and here's our 4K resistor. So we're just going to write this as a single mesh circuit. It can be, if you're solving for the current, you could take the total voltage and divide by the total impedance. So that would be this right here. So the current is the voltage divided by the total impedance. So fortunately, because of the way the voltage source transforms and the way the algebra works, we actually have a function that looks mostly already factored, or at least close to it. So need to work with this one a little bit to figure out what its roots are, and then this one obviously can't be factored any further. Okay, so this is just me generating this function so that I can do some stuff with it later, like a partial fraction expansion. So I define the numerator as 240, 0, and 0. That gives me 240 s squared in the numerator. And then I had to define the denominator in two parts. So if we come back, we had this term and this term, and I didn't want to do that algebraic multiplication by hand. So I input this one as denominator 1, and I input this one as denominator 2. And then you use the term convolve to multiply two polynomials in MATLAB. And then I used the function TF, numerator comma denominator, to create this as a transfer function in MATLAB. We'll talk about transfer functions in next week's lecture. Next week is all about transfer functions, but I think you get it that in MATLAB, in order to generate this polynomial, you have to define it as a transfer function. Do you have to generate the polynomial? No, you don't. It's just kind of useful, and the reason it's useful is it just allows you, to look at your function and make sure it looks like you expect it to look. Okay, so from there, in your book, they just show the partial fraction expansion. So this is not really the way that I would do it. I would take the s squared plus 40,000 squared, and I would do an as plus b in the numerator, and then I would take this expression, once I could tell it didn't factor into real roots, and I would do I'd complete the square. And I would do that as opposed to the technique that they show here if I were working this by hand. But I'm not working it by hand, so I did it on MATLAB, and I used the residue command, and here's my numerator comma denominator. I think if you've defined a transfer function, you can maybe put h here. I don't remember. Anyway, you define an array R, P, and K where R is roots. For the R is basically the what's in the numerator. P are the poles, and then K is if your numerator is of a higher order than your denominator, MATLAB will generate those terms. Now, in our case, our numerator is of lower order, so our K is going to be an empty set. P are the poles, those are the roots for each part of the denominator, so let's look at those. This is all times 10 to the 4th. So this is J 40,000 and this is minus J 40,000. So that corresponds to this one and this one. And then this is our first complex root and this is our second complex root corresponding to this one and this one. So one thing that you want to be sure you do is you want to be sure you put this in order of how MATLAB gives you the poles, because your numerator is going to go in the same order. So you notice this first term, it's always going to be s minus the root. So it's s minus this, and then this term is s minus this, and so on. So then from MATLAB, you're actually already given your k's because it calculates those for you. So you notice these are the complex conjugates. So it's giving you K1 is this first term. And so that's 0.0019. They did a significant digit thing in your book and got 1.875, so that's okay. The number of significant digits that your book uses is sometimes a little bit silly. I know in the homework they ask you to use a certain number of significant digits. I think I input tolerances in the homework so that it would count the 0.0019 as okay. But as you know, in MATLAB, you do have the ability to set the number of significant digits in the answer. So you could just override the default here and get more significant digits for R if you so chose. Anyway, so this first one, which is 1.9 times 10 to the minus third, that's your first, that's your K1. And then your 1.9 times, and then this is K1's complex conjugate. In this case, it doesn't matter because there's not an imaginary term. Okay, so then your second expansion, which is the one on the complex conjugate pairs, K2 will be this first term, and then this is K2 star. So those are what go in the K1, K2 positions. So once we have K1 and K2, there is a table that was presented in the slides from last week that showed these 4 useful inverse transforms. So once you have in this form, you can then transform that easily into, first of all, a cosine function, and then with a phase shift, and then a sinusoidally damped cosine function also with a phase shift. In the first case, because you didn't have any imaginary component, that cosine function didn't have a phase shift. In the natural response part, it does have a phase shift. So one thing to also point out is that in the solution, you have a cosine function part, and this constitutes what would have been the natural response of the system. I'm sorry, it would be the forced response of the system in differential equations. There will always be a term in your answer that looks like your source. So if you have a sinusoidal function for a source, you're going to have somewhere in your solution a sinusoidal function. And when I say sinusoidal, I mean in the general sense, sine and cosine. It may be phase shifted, but you will have that sinusoidal function, because if you think about what happens as this circuit settles into the steady state, it looks like an AC circuit. And then here is your here is your natural response. So this part is a function not of the source, but only of what's in the circuit. And so the natural response here of this RLC in this particular case is an exponentially damped cosine function. So when we do AC circuits, we always just analyze them as phasors, and we neglect the initial conditions or any transient effects of actually turning on the source in the system. So what this problem does is this models, if you do have a sinusoidal source, yes, here's your, this would be what your output would be if you did like a phasor type analysis. But if you want to incorporate the transient effects, you can only get that when you use Laplace. And so what the Laplace method shows is there is this exponentially decaying term that is a function of the values of R, L, and C. And this will die away. This one won't. So eventually a phasor analysis would be great. But in this particular case, you do have this this transient term that's an effect of anytime you turn on a source to a circuit that has energy storage elements, there is some transient effect of the electric and magnetic fields building up in those elements. So I thought this was an interesting problem, and I thought it was worth going through because it does show where, you know, even with a sinusoidal source, there are some transient effects. Now, oftentimes in like a 60 hertz circuit, so let's say that our initial, our frequency of our source was closer to 60 hertz. A lot of times what you'll find out is that this decay rate is so rapid that it literally is buried in the first cycle of the cosine function. And so that is why in AC analysis we can use phasors and ignore the transient effects. However, in other systems, if the frequency here and the decay rate here are of a similar order of magnitude, then you will be able to actually physically see those transient effects. I should have actually plotted this on MATLAB for you so that you could see what this looks like, and I may try to do that and post that later, or that's something that you can do, input this function into MATLAB and see how that plots out. Okay, so here is the result written a little more clearly and bigger. And notice we always want to put our step function. I'm pretty forgiving on exams because I have to be honest. A lot of times I forget to put the U of T when I'm lecturing in class or when I'm, making out example problems. It should always be there because obviously this circuit didn't exist for t less than 0. Okay, and then they do recommend, you could use phasor methods to verify this result. Kind of. You can verify this first part. You won't see this second part with the exponential decay because it is a transient response. Okay, so that concludes the examples that I wanted to look at for just simple single mesh or single node circuits. And we'll look at one more thing, which is a multiple mesh RL circuit. Now, don't look much at this because I don't do a lot of this for no real reason other than the algebra gets pretty complicated, and what I really want you to learn in this section is how to transform circuits and how to do the inverse transform to get the solution and how to incorporate initial conditions. But this is a fairly simple one, so I think this one is worth looking at. So in this circuit, there's no initial stored energy. Both initial conditions are 0. And then the switch closes and this voltage source is applied to the circuit. So we're going to obviously transform the currents I1 and I2. We're going to transform the inductors to impedances SL. And this voltage source is going to go to 336 over S. So here's the voltage source. Because since there was a switch, we put a U of T in there to define it in the time domain. Okay, and so here is our circuit for t greater than 0. So for t greater than 0, everything is closed. We have two meshes. And so we just write two mesh equations. So the first mesh equation is given here, and they've done a little simplification and presented these kind of in a final and simplified form. So if you need assistance in writing those mesh equations, you can ask me about that. But if you write the mesh equations and then you combine similar terms, these should be the two equations that you get. Now what they're going to do is we're going to place these in matrix form and use Cramer's rule to solve. So here's what delta looks like in matrix form. Remember, that's the coefficient matrix of or the coefficient determinant of the equation. And then remember, in Cramer's rule, we would take, to solve for the first current, we would take the determinant where we have the first column replaced with the column on the constant side. And then to solve for the second variable, we take the second column and replace it. And then Cramer's rule says I1 is N1 over delta and I2 is N2 over delta. If you don't remember Cramer's rule, I do have a set of notes that I posted for my Circuits 1 class. And if you would like to be linked to that, then just please request that and I can link you to that. I did do a little thing on MATLAB to see if it would do the algebra for me, and it actually does do the algebra beautifully. So I defined S as a symbol, and then I created the delta matrix right here, and then I asked it to do the determinant of delta, and it gave me an answer, gave me this answer. Didn't factor out the 84, and it didn't factor. But what you could do if you wanted to get to this point is you first of all could divide this by 84 so that the highest order term has a coefficient of 1, and then you could take those coefficients, enter them not as a symbol but into just a polynomial matrix and ask it to find you the roots, and then you would get this out of MATLAB. So taking then N1 and N2, dividing by the delta term, this is what you get for I1 and I2. So each of those will need a partial fraction expansion. So when you do the partial fraction expansion, you get this expression for I1 and I2 respectively. And then taking the inverse transform, you end up with the following. Okay, I want to comment on the functional form and a little bit about sort of the physics of what's going on here. So let's go back. You notice, first of all, I want you to look. You notice, first of all, we have like a DC term or a constant. And then we have two different exponential decay terms with two different time constants. This one being 1 over 2, and this one being 1 over 12. So let's go back and look at our circuit. If you look at our circuit, we have two inductors, and these two inductors cannot be combined. And so you know, of course, in a simple RL circuit, you're going to get an exponential transient effect with a time constant, and that'll be like a L over R time constant, and that's what's going to sort of define the natural response of the system. In this case, we have two inductors, and they can't be combined. So what happens is, if you have multiple energy storage elements, you can end up with multiple time constants. So in this example, we can see there's one time constant. There are actually two time constants. That's because you have two different inductors. Now, almost always, one of them will dominate, and it'll be the slower part of the circuit that dominates. The rapid part of the circuit, the transient effects go away pretty quickly. So this e to the minus 12t, you can see that, in very small amount of t, this term becomes very small and doesn't contribute as much. On the other hand, it takes this one 6 times as long to decay away. So this is going to be the probably the dominant term as far as how the function looks in the time domain. Once again, I wish I had plotted these because I think it's important for you to realize this is not just about the mathematics of finding the numbers. It's about thinking about what the circuit's doing. So what this circuit is doing is, if you look here, as t goes toward infinity, these transient terms die away. And you have 15 amps or 15 microamps. No, I guess 15 amps in one loop and 7 amps in the other. And so you are approaching DC where the inductors look like a short. What the Laplace tells you is that you've got these functions added on. So this defines how it actually approaches the DC term. So it makes sense, my answer makes sense that it's going to approach the DC term in this way. It's got two time constants because I have two inductive storage elements. If I had a third out here with an inductor and a resistor, these are ladder networks. They're called ladder networks. If I had a third out here, I'd get even a third time constant. So the number of, and I would get a higher order differential equation. I'd get a higher order polynomial in S. So it would become quite a bit more difficult to solve. So that concludes what I want to show in this example, as well as the example videos for using Laplace analysis in circuits. And we'll move on in the next section and talk about transfer functions, which is also using Laplace in circuits. It's just with a little bit of a different focus.